Kirchoff's voltage law, which is also known as the loop rule, is a bit more complicated, but it boils down to the idea that the potential difference around a closed loop is equal to 0. And I'll again go through an example to show you how this works. And so I'll draw the circuit out, and then there are 4 key points that I'll list for you to take a look at, and then we'll go through and I'll actually apply the loop rule. So this circuit has 3 EMFs, 1, 2, and 3, and 3 resistors, 1, 2, and 3. And the first key point is to show the current direction for each element on your circuit diagram. And I'm going to show the current directions in red, and I'm just going to assume that the current through R1 is going up, so I write I1. I'm going to show that as well through the EMF. And then once it hits that top wire, it would actually move to the right, so we have I1. And then if I look at the bottom wire here, I would see that in order for that to be consistent, I1 would have to go left along the bottom wire, then up through R1, then through the EMF1, and then to the right. Looking at R2, I'll just say that the current through R2 is also going up, and then I have the current going up through the second EMF, so that's also I2. And again, R2 and E2, or R2 and epsilon 2, the second EMF, are in series because all electrons that go through one have to go through the other, and that means that they have the same current. Then for R3, I'll just be consistent, I guess, and have I3 going up through R3, which then means it would have to go to the left through the third EMF, and it would have to actually have come going right from the bottom wire. So it's important when you label the current that it's consistent. The current in one branch or in one set of wires, set of elements in series, has to be going in the same direction. And when you're just starting out, it's handy to draw it for each element, but with a bit of practice, you could probably just draw the current I1 once, I2 once, and I3 once, instead of, say, 3 times here for I3 and 4 times for I1. That just comes with practice. Now, the second key point is that you have to show the loop. Kirchoff's voltage law requires that you actually look at a loop, a closed loop, to get delta V equal to 0, and you have to show the loop on your diagram. And I should really say loops because typically you'd have more than one loop. So for example, the first loop that I'm going to look at will be in the left sort of circle, the left region here. And what I like to do is actually to draw this in a different color. So I will have this loop going clockwise, starting in the top left, and then going down through R2, down through the second EMF, and then up through R1 and up through the first EMF. And I'd like to label that. I'll call that loop 1. Another way that people often label these is to label the junctions. So if I have A, B, and then C along the top, and then I'll have D, E, F along the bottom, then loop 1 would start at A. So I could say loop 1 is A, B, E, D, A. And again, it's a closed loop. So using the letters like that helps you remember that you're doing a closed loop, or verify or confirm that you have a closed loop because you start and end at the same point. Now, before I get into the example of the first loop equation, I have to describe how you handle the circuits, because you basically trace along. You could imagine tracing with your finger or just imagining. You trace along the loop, and when you encounter an EMF, you handle it a certain way, and if you encounter a resistor, you handle it a different way. So when you cross an EMF, you're going to add to your equation, and the only question is whether you add positive EMF or a negative EMF. And it turns out that when you cross it, if you're going in the direction of the loop and you cross from negative to positive on that EMF, then you add plus epsilon. If you're going from the positive terminal of the EMF to the negative, then you add negative epsilon. And there's a similar but different rule for resistors. So when you cross a resistor, if you're going in the direction of current as drawn by you on your diagram, you add negative IR to your equation. And if you're going against the current, you add positive IR to the equation. Loop 1 starts at A, goes to B, then down to E, then to D, and back to A. Closed loop, starting and ending at A. And I personally prefer to draw it, but I can really understand how people like to label the different points on the circuit to make it very clear. So if I start at A, when I go to A to B, there are no elements. It's just a wire. So there's no change in potential along a wire. Going from B to E, first I reach R2, and I'm going against the current I2. So I need to add plus I2 R2 to the equation. Then I reach the second EMF, and I'm going from positive to negative, so I'm adding negative EMF 2 to my equation. Then I get down to E. From E to D, there's nothing. Then from D to A, I'm going across R1 in the direction of current, so I'm adding a negative I1 R1. And then I reach the EMF 1, and I'm going from the negative to the positive terminal of the EMF, so I have to add positive EMF 1. And it's a closed loop, so the delta V across that loop is equal to 0. And this forms one of the equations that I can use to solve this circuit. Basically, with these circuits, you end up with a certain number of equations, a certain number of unknowns, and hopefully you have the same number of equations as unknowns, and then you have to solve for whichever variables are missing. Often it's current, but sometimes you have to solve for an unknown resistor or EMF or something else. I'll do 2 more quick examples of the loop rule, and then I'll go through 2 quick examples of junctions, and that'll be it. So for the second loop, I'm going to start at E, and I'm going to again go clockwise and end up back at E. So this would be loop 2. So if I'm using the labeled junctions, then I start at E, I go up to B, across to C, down to F, and then back to E. So starting at E, I'm going up across the second EMF, so I have plus epsilon 2. Then when I reach the second resistor, I'm going with the current, so I can write minus I2R2. Then from B to C, I'm going against the EMF from positive to negative, so I say minus epsilon 3. Then from C to F, I'm going against the current I3, so I have plus I3R3. And then I get back to point E. So that's the closed loop, and I get that equation equal to 0. For my third loop, I'm going to go around the outside. I'll start at C, and then go clockwise again, all the way around. Sometimes people call this the big loop. So I'm starting at C, then I go to F, then to E, then to D, then to A, then B, and finally C. So this time, I'm going against I3R3, so I have plus I3R3. From F to E, there's nothing. From E to D, there's nothing. From D to A, I'm going in the direction of the current I1, so I have minus I1R1. Then I'm going up the EMF from negative to positive, so I have plus epsilon 1. Then going from A to B, there's nothing. From B to C, then I'm going down that EMF 3, so I have minus epsilon 3. And I'm back at C at that point, so the loop is closed, and I can write that it's equal to 0. This example has 3 loops, but when you try to solve for these equations, you find out that the 3 equations aren't independent. They're dependent on each other. And what that means then is that you actually have to also consider the junction. So I'll take a look at junction B. And remember, for the current rule, we said that the current in is equal to the current out. So at B, I have I1 going in, I2 is also going in, and I3 is also going in. So I have 3 currents going in and no current going out. So the equation I get is I1 plus I2 plus I3 is equal to 0. So this is an example where this isn't really possible for all the currents to go in and then have nothing come out. So it turns out that when I drew this, at least one of these currents would be in the wrong direction. And that's okay. I don't have to restart the example. I don't have to do anything differently. It's just that after I solve for the missing variables, I will find out that one or more of the currents is a negative number. And then it turns out that that particular current is going opposite to the direction that I've drawn. You don't have to restart anything. Just for completeness, we could also look at junction E. And again, if we're looking at the current in equal to the current out, It turns out that there is no current in. I1, I2, and I3 are all going out of E. So I have 0 current in equal to I1 plus I2 plus I3 going out. This is another example where we have two different junctions with 3 or more wires. We basically ignore all the junctions that only have 2 wires because that ends up just being very ridiculously simple. If you look at junction A, for instance, you would solve that I1 is equal to I1, which is not helpful. So we only look at junctions, only consider junctions that have 3 or more wires. And in this case, in this circuit, there are only 2 junctions, B and E, that have 3 or more wires. And remember, with the 3 loop equations, I told you that it turns out they're dependent. You only get 2 independent equations when you have 3 loops. There's a similar issue here where you only get 1 independent equation when I have 2 junctions. And you can kind of see why, because both junction equations are identical. You have all 3 currents equal to 0. You have the sum of all 3 currents equal to 0.